record. Okay, so in today's lecture, I want to focus on a few things. We're still on the topic of alkanes, now that we know a little more how to name them, now that we understand a little more about their properties, about their reactivity, such as it is. They don't undergo a lot of reactions. Today, I want to get more into the nitty-gritty of the structure of alkanes, in particular, how the atoms are arranged in three-dimensional space and ways in which the structures can move or rotate around single bonds. And that's really one of my main points today, which I think I also made in the class notes, that you mustn't think of a molecule as being like this stiff, rigid, unmoving thing, like a piece of furniture. Molecules are in constant motion. They're in motion through space. They bounce off the walls of the container and bounce off of each other. Certainly, if we're talking about liquids or gases, that's definitely the case. There is always constant rotation around single bonds, at least to the extent that that's possible within the constraints of the structure of the molecule. And the two main molecules I'm going to focus on are ethane, because if you understand the conformations of ethane, I think you understand most of what you would need to understand the conformations of larger, similar alkanes. And then the other one we're going to focus on to some degree is cyclohexane. And that's what we're also going to talk about today is cycloalkanes in general, as well as this issue of cis and trans stereoisomers. That's something we'll have to deal with in terms of cycloalkanes. And then later on in the next chapter, we'll also deal with cis and trans stereochemistry in alkenes, which is conceptually kind of like the idea with cycloalkanes as well, and also conceptually subtly different. But I think if you understand one, it becomes reasonably easy to understand the other. So that's basically the plan for today. So last time we finished off talking about how alkanes react with oxygen via combustion and also with halogens, chlorine and bromine. And you can get these substitution reactions by substituting a hydrogen for a chlorine or bromine atom. And we talked about the ideas of how there can be multiple different possible monohalogenation products. I was just looking at the OWL assignment, and I know there are some questions about that. So that's the issue that it's getting to. Before I get into conformations of ethane, I also did want to get up here the definition of stereoisomers and conformers, since actually the book is wrong, and I'm really rather shocked about this. It's the first time I've seen this mistake in an organic chemistry textbook. They're saying that conformers are stereoisomers, and they are not. The book is wrong about that. So I mentioned that also in the class notes. Please be sure you've got that straight when you read the textbook, because they are lying to you at that point. Conformers are not stereoisomers, because stereoisomers is a relationship between two or more different molecules. Stereoisomers are isomers like constitutional isomers are, but whereas constitutional isomers have the same formula, but a different connectivity, the atoms are connected differently. Stereoisomers have the same formula and the same connectivity. The atoms are connected in the same way, but they're arranged differently in three-dimensional space in such a way that you can't just turn one of them into the other just by rotating the molecule or rotating around single bonds. Conformers, on the other hand, are kind of different instances of the same molecule. So conformers are two or more molecules of the same substance that you can just interconvert just by rotating around single bonds. And what we're going to find with ethane is there's just two conformers or two conformations. So that's what we're going to get to next. So let's see. Maybe I'll finish my drawings over here before we start playing with my Tinker Toys, which I did bring my I brought part of my molecular modeling kit. I thought of bringing over the entire box, but I said, you know what would have happened if I'd done that. 100% chance I would have dropped it and there'd have been little balls and bonds everywhere. So I just brought only the ones I think I will need, and that seems to have worked. Good. So ethane, of course, you're familiar with the structure of ethane. ethane is two different conformations depending on how we rotate around the carbon-carbon bond. And I've just labeled two of the carbons green just to correspond with my molecular model. And I only did that just so it would be easier to see. I wasn't trying to imply that there's anything special about those two particular hydrogens. I just thought it would make it easier to see. So this is one of the conformations, and we call that the staggered conformation. I think I'll write that in black, though. Two different views of the staggered conformation. And then there's another one that we call the eclipsed conformation, which has a different orientation around that single bond. And you'll notice I'm also indicating some of the bonds with wedges and dots. So these wedge bonds, like I'm drawing one right now, those are coming out of the plane of the screen at you. And the dotted bonds, like this one here, are going back into the screen. And what I'm trying to do here is to reflect the bond angle that we would expect in an sp3 hybridized atom, which is somewhere around and about 109.5 degrees. And I always say the same thing. I always say to my students, we have a mutual agreement here. I won't get out a protractor on you if you don't get out a protractor on me. But I think you'll agree that I could quibble about this hydrogen. I think I can do a little bit better with that one. But I think you'll agree I've made it so that you can see these bond angles are definitely more than right angles. They're definitely greater than 90 degrees, and I'm aiming for 109.5. And I think you'll agree with these structures. I've put in a good faith effort at getting somewhat close to 109.5. That's all I would ask about. That's all I would ask for you guys. Just give it your best good faith effort. And so this is one way of drawing the eclipsed conformation. The other way that goes, we call it a Newman projection, is kind of looking edge on. And I'll show you both of these when we play with our molecular models in just a moment. But the reason they call this the eclipsed conformation, actually, I realized I wanted to make that one green, is because the hydrogens are directly in front of and behind each other. Let's see. No, not that one. This one's, I think, a little easier to see. There we go. Good. So those are the two conformations of ethane, and those are the only two conformations. Because if you turn the molecule anymore, then you wind up with just another version of one of the other ones. So let me see if I can make this look like the top one. Maybe something like this. Whoops. I'm here trying to make the front hydrogen sort of sit between the two back hydrogens. So something like this, I think, would be similar to my drawing on the top left. So there they are in the staggered conformation. And in the staggered conformation, essentially, any two hydrogens on opposite sides are going to be 180 degrees apart from one another. So that's one of the conformations. And then the other conformation would be the eclipsed conformation, where instead, did I do that right? Oh, I forgot to make them green. I'm sorry about that. We'll leave that over there in the meantime. I actually do worry that might make things worse, but we'll do it anyway. You know what they say, no good deed goes unpunished. Good, so I think you can see how these two hydrogens now lie in the same plane, so that one is directly behind and in front of the other. And same thing with these two over here, same thing with those two over there. So we call that the eclipsed conformation. It's even a little easier to see when you look at it directly edge on. Something like that. There we go. And so that's what I'm trying to show over here. And I think I said we call those Newman projections. Not that I really care if you know who they're named after, but this is just another way of showing the same thing. And we're trying to show that these 3 hydrogens are connected to the carbon in front. And there's also these 3 bonds that are kind of broken up by that circle. And so those are the bonds that are in back. So that's just another way of showing the same thing. And I'll be honest, there's yet a 3rd way to show these. I don't want to trouble you guys with this. I think this is enough to get the idea across. There's also Solwers projections. I mean, you can just go nuts with this. You're beating it to death at that point. But these are the 2 different conformations. And you can tell they're different by looking at how the atoms are arranged in space. So if this is an eclipsed conformation, if we turn 60 degrees, now it's going to be staggered, another 60 degrees and it's eclipsed again, another 60 degrees and it's staggered again, and get my hand out of the way, another 60 degrees eclipsed again, and another 60 degrees staggered again. So, and again, I wasn't trying to imply anything special about those hydrogens that I made green. I just thought it would make it easier to see what was going on, particularly when you're looking at the molecule from the side like that. I just think it makes it a little bit easier to see. But that's a staggered conformation. This is also a staggered conformation. And so those are the only 2 conformations of ethane. As it turns out, it's the eclipsed conformation that's higher in energy. And remember, higher in energy means less stable. Let me write that down. In green, apparently. If you have 2 or more species, or if you have 2 species where one is higher in energy, that means it's less stable. And lower in energy means more stable. Just a review from Gen Chem. So the eclipsed conformation is higher in energy. And we'll go over why in just a second. The staggered conformation is, of course, lower in energy. And the reason for that, which we somewhat lose a little bit with these molecular models, is in one of these eclipsed conformations, any 2 hydrogens, there we are, any 2 hydrogens that are directly in front of and behind one another are closer together in 3-dimensional space than they really have to be. And so they're kind of bumping into each other. Really, when you use a molecular model kit like this, the bonds are not in proportion. Sort of the atomic nuclei, if you will, are much larger than these bonds would suggest. And if we wanted to make this look a little more accurate to life, we would have either the bonds being shorter or the balls that are the atoms being larger. And so these 2 hydrogens, although they're not connected directly, there's a few bonds in between them. They're closer together in 3-dimensional space than they need to be, and that problem is relieved in any of the staggered conformations. Now they're a little further apart. So that's why the staggered conformation is higher in energy. And the amount by which those 2 differ in energy is known. I really don't care if you memorize the number. I think it's roundabout on the order of 20 kilojoules per mole or something like that. But like I said, I really don't care if you memorize that number. But the point here is that we have these different conformations. But again, this was also the point I was making before. The staggered and eclipsed conformations are not stereoisomers. This is the same molecule we're talking about here. So again, when the books, I can't imagine how that made it through the editing process. If some guy at some university can pick that out so easily, I just can't imagine how that made it through the editing process. But absolutely, conformers are not stereoisomers. And we'll get to stereoisomers today also, in particular in the context of the smaller cycloalkanes and cyclohexane as well. And I wish I had time to do some examples of naming cycloalkanes. I'll just let you know the idea behind naming cycloalkanes is very much the same as the idea behind naming alkanes. If you can name one, you can name the other. I always wish I had time for a whole bunch more examples, but I have to kind of pick and choose the topics we cover in here. Good, so actually, I think that's just about all I really need to say about ethane. Just let me make sure I'm not missing anything really obvious. Well, I guess I'll just say, in any given sample of ethane, you need to understand all ethane molecules are constantly rotating around that carbon-carbon bond at all times. And so they're always going staggered, eclipsed, staggered, eclipsed, staggered, eclipsed at all times. And since we know the energy difference between eclipsed and staggered, if we wanted to, which I know we don't, but if we wanted to, we could plug that into our what? Equilibrium constant is minus RT net, no, e to the minus RT over delta G, no, delta G over minus RT, that's what it is. And we could plug it in and figure out what the equilibrium constant is. In other words, what the ratio of staggered is to eclipsed. None of us is interested in doing that right now, I don't think. I'm not very either. But we could if we wanted to. All that stuff is still there. But that's basically just the nature of these molecules. So again, one of the main points here for this first part of the lecture that I'm trying to get across is just remembering that molecules are in constant motion. They don't just sit there stiff and rigid like this. Both moving through space and wherever possible, rotating around single bonds like that. And that leads to this property called conformations that lots of these alkanes have. And we could have gone up, we could go up even from ethane to propane, and you would find the exact same two conformations, except one of these hydrogens would be replaced with a methyl group. And so sometimes the methyl group would be eclipsing the hydrogen in front, other times it would be in between, it would be staggered. So propane is the same two conformations, and we would still expect the staggered conformation to be lower in energy, the eclipsed conformation to be higher in energy. Things get a little bit trickier when we get up to butane, because when we get to butane and you're looking down that central carbon-carbon bond, now there's two different eclipsed conformations and two different staggered conformations. But the concept is no different. So I really think if you understand ethane, that's probably going to carry you through at least at a conservative estimate, like 85%, if not more, of anything you'll need to concern yourselves with in terms of conformations of alkanes. Probably more. I just wanted to give a conservative estimate. So much then for conformations of ethane and other alkanes. We also today need to get into the cycloalkanes, which we haven't talked about very much. And certainly the three smallest cycloalkanes we could draw pretty easily. So here we have cyclopropane. We just use that prefix cyclo to show that we're dealing with a cyclic compound. This one would be cyclobutane. And finally, cyclopentane. We can deal with these three very quickly because they're not nearly as interesting in terms of conformations. There's much less to say about them. And then we'll enlarge a little bit on cyclohexane, about which we'll have quite a bit more to say. But those are the three smallest cycloalkanes. I think you'll agree you need to have at least 3 carbons to have a ring, right? There's no such thing as a 2-membered ring. You need at least 3 carbons to make a ring. So those are the 3 smallest cycloalkanes. Let's see. We run into certain problems. Remember that, again, that ideal bond angle for an sp3 hybridized atom is 109.5 degrees, give or take, somewhere in there. And I think you'll agree with both cyclopropane and cyclobutane, we've got a problem. Those angles are significantly less than 109.5 degrees. In the case of cyclopropane, that bond angle has to be 60 degrees. By definition, it has no choice. The molecule is going to be in the shape of an equilateral triangle. And using my molecular models over here, I cannot even make you, I'd have to use different special stretchy bendy bonds in order to show you what cyclopropane looks like, because these bonds would break over here. And here I'm about to try to build my cyclohexane while talking about other things. So I'm trying to multitask. We'll see how this goes. And likewise in cyclobutane, you might guess on taking a look at cyclobutane that the bond angle is 90 degrees. It actually is a little bit more than that. It actually is a little bit more than that. Cyclobutane is actually puckered a little bit. If I wanted to draw it a little bit more true to life, it might be a little bit more like this. So that didn't turn out so well, did it? I'm kind of exaggerating over here, but a little something maybe like this is a little closer to it. Something like that. And I don't remember the exact bond angle in cyclobutane, and I sure don't care if you've memorized it. But I think you'll find it's something like 94 or 95. It's a little bit more than 90 degrees, but still pretty far away from the ideal bond angle of 109.5. And as you can imagine, that's going to make the energy of these molecules go way up compared to other cycloalkanes, because it's so far away from 109.5. And that phenomenon goes by a couple names. One name that it goes by is angle strain. That's an increase in energy due to bond angles being very far away from the ideal. Whoops. Very far from ideal, which in the case of alkanes is going to be 109.5. It's also sometimes called ring strain. Same thing. There you go again. We organic chemists seem never to be happy unless for any given concept, there's at least two different words for it. I don't know why we're like that, but we are. So angle strain or ring strain. So both cyclopropane and cyclobutane have significant ring strain. I'm trying to see where I'm missing a bond. Over here. Good. And so I've got my cyclohexane ready. Well, actually, I can show you what cyclopentane looks like, because cyclopentane now has enough of that angle strain removed that I can actually build a model of it. And so again, I'm not trying to imply anything in particular with the green hydrogens and the red hydrogens. However, I think it would look nicer if all the green hydrogens were on the same side and all the white hydrogens were on the same side. So maybe I'll go like that. So there's your cyclopentane. Cyclopentane actually is not perfectly planar. It's a little bit puckered. So it's not a perfect pentagon, but it's a little bit puckered or envelope shaped in 3D space. And I would say cyclopentane has almost no angle strain, very, very, very little, a teeny bit. But the bond angles are extremely close to 109.5. So it doesn't have nearly the same problems as cyclopropane and cyclobutane do. Those molecules are, as you might guess, much more reactive and much higher in energy on a carbon per carbon basis than either cyclopentane or cyclohexane. And that comes about again because those bond angles are so far away from the ideal. Cyclobutane does its best by being not a perfect square. It puckers a little bit out of the plane, but there's only so far it can go. And the bond angles are still nowhere near 109.5 degrees. So in cyclopentane, we've got that problem almost solved, 98% solved or something like that. Cyclohexane is special. That's the first of the cycloalkanes that has no angle strain whatsoever. No angle strain, none of the so-called torsional strain that you also can get with these molecules, nothing like that. So that I think is enough to say about those three molecules for now. I also want to cover this whole business of cis and trans stereoisomers. So we'll cover that next before we get into cyclohexane. Any other questions on, besides the cis and trans thing, that is, on the smaller cycloalkanes, on the conformations of ethane, things like that? All right, well, let me do this then. And again, you can always feel free once I've uploaded this to YouTube to stop on the full screen and if in case you missed anything. But I unfortunately do need to clear the board. So this also gets back to the idea of stereoisomers. Let's get to our first example of compounds that are stereoisomers. And maybe I will draw, can I do it? No, not quite with my models, but let's take cyclobutane and we'll consider two different 1,2-dimethyl cyclobutane.